Welcome back to the course entitled Elementary Electrochemistry. We have now reached the third week of this course. So in today's class we are going to discuss about the electrode potentials and how one can express electrode potentials of different electrodes using the Nernst equation. So we are going to discuss about the electrode potentials today. So as we know that in a given cell, the sum of two chemical reactions occurring at the two electrodes represents the cell reaction where there is oxidation and reduction taking place at anode and cathode respectively. So the EMF, the electromotive force of the cell, which is written as E cell, is calculated using the Nernst equation. So each half cell has its own potential called the electrode potential, right. So when you have a cell, you have two half cells, and using Nernst equation one can calculate from the half cell potentials the EMF of the cell. So let us take a few examples. Let us take the first example A, when we have a zinc rod dipped in a solution of Zn2 plus and consider it as oxidation. So the electrode is written as Zn2 plus aqueous. This is how you write the electrode, and the corresponding reaction that we are talking about is Zn getting oxidized to Zn2 plus 2 electrons which are released at the electrode. So if E Zn and E0 Zn denote the electrode potentials of Zn dipped in Zn2 plus solution and the activity of Zn and Zn2 plus are denoted by AZn and AZn2 plus respectively. Then you can use Nernst equation and write the relationship between Ezn as E0Zn minus RT by 2F, because there is 2 electron transfer, Ln activity of Zn2 plus divided by activity of Zn, right. So now when we are talking about a pure metal zinc, one can assume activity of Zn to be equal to 1. So then this equation can be modified as Ezn is equal to E0Zn minus RT by 2F Ln activity of Zn2 plus. So E0Zn is the electrode potential of zinc in a standard solution of Zn2 plus ions of unit activity, that is activity of Zn2 plus is also equal to 1. So this E0Zn is called the standard oxidation potential of zinc electrode, right. So when you write it as oxidation potential, and if the value turns out to be positive, then when you write it in terms of reduction potential of zinc, the value will be nothing but negative, because the opposite reaction is considered, right. So in case of a Daniell cell where this Zn electrode is used as a cathode, where reduction takes place, that is Zn2 plus by taking 2 electrons gets converted to zinc and gets deposited at the electrode. Then in a cell like potassium amalgam, K plus in aqueous medium is in connection with Zn2 plus aqueous with metallic zinc as electrode. Then the electrode potential for Zn will be considered as the reduction potential of zinc. So, this is just positive and negative when you consider the forward or the backward reaction. So, when you try to write E0 Zn slash Zn2 plus, so that I am showing the reaction is in the oxidation direction, the potential is reported to be 0.761 volt, whereas when you write the E0 Zn2 plus getting reduced to Zn in the reduction direction, then we would write this value as 761 volt. So, one has to remember whether you are writing the electrode potential in the oxidation direction or in the reduction direction, and accordingly this sign will be used. So, let us see the second electrode, which is a gas electrode. So, one of the important gas electrodes that we encountered is the chlorine gas bubbled around a platinum electrode is in equilibrium with a chloride solution. This is the electrode, and the corresponding reaction is Cl minus getting converted to chlorine gas releasing one electron, and it is written in the oxidation direction, right. So, when we write E0 Cl minus Cl2, one should write as this is not 0, this is not the standard state, this is the electrode potential of chlorine chloride system with a given concentration of chloride in solution, and this is the standard value, which is Cl minus to Cl2 minus RT by F ln activity of half Cl2 by activity of Cl minus. So, now this is the oxidation potential, and this is the standard oxidation potential. So, if we assume the activity of pure chlorine gas is to be equal to 1, one can rewrite this equation as E Cl minus Cl2 is equal to E0 Cl minus Cl2 minus RT by F ln 1 by activity of Cl minus. So, this is for a given solution of Cl minus of known concentration, from which one can calculate the activity of Cl minus, right. So, similarly, one can consider the oxygen electrode. So, this oxygen electrode is again oxygen gas is bubbled around the platinum electrode, and it is in equilibrium with OH minus, and the corresponding reaction is 2 OH minus giving you H2O plus half O2 plus 2 electrons. So, the electrode potential that one can write is OH minus going to O2 is equal to E0 OH minus going to O2, minus RT by 2F ln activity of half of O2 divided by activity of OH minus, and then when O2 is passed at 1 atm, one can assume that activity of half O2 is nothing but equal to 1, and then you can write this E OH minus to O2 is equal to E0 OH minus to O2 minus RT by 2F ln. So, one can make it plus and write AOH minus, because see here AOH was in the denominator, and then when you take it to the numerator, then it becomes the plus sign. So, this is how one can very easily write the half cell reactions and the corresponding electrode potentials. So, we also learnt about the silver chloride electrode in the previous lectures. So, we should also try to write down the same equation for AgCl electrode. So, what is the electrode here? The electrode is Ag in connection with AgCl in solid and in equilibrium with chloride ions in solution. So, the cell reaction will be Ag plus Cl minus getting converted to AgCl as a precipitate, releasing one electron. So, here again it is the oxidation of silver. So, that is we are writing in the oxidation direction. So, then what one can write is half cell potential. In the oxidation manner, one can write E AgCl equal to E0 AgCl minus RT by F, because one electron transfer, ln activity of AgCl divided by activity of Ag into activity of Cl minus. Or one can write this silver activity of pure silver taken to be 1 one can write this equation as E Ag AgCl equal to E0 Ag AgCl minus RT by F ln activity of AgCl divided by activity of Cl minus. So, this is how one can write the cell reaction for silver chloride electrode. Now, if we try to write the EMF of a cell from the electrode potentials. So, let us take the example of Daniel cell. So, where we write the electrodes as zinc in equilibrium with Zn2 plus in aqueous medium, then you have copper 2 plus in aqueous medium and Cu as the electrode. So, here the right hand side, this copper 2 plus electrode is the positive electrode and the left hand side is the negative electrode. So, the EMF of the cell is obtained by subtracting the oxidation potential of the positive electrode from the oxidation potential of the negative electrode, right. So, therefore, one can write E cell is equal to E ox of the negative electrode minus E ox of the positive electrode, or in other words E ox left minus E ox right. So, left minus right in the oxidation direction. So, then in the reduction direction what will happen? One can replace E ox by E red. So, one can write E red with a minus sign and left minus of minus E red of right. So, overall it will become E reduction of right minus E reduction of left. So, it depends on how you consider. If you are considering the oxidation potential, then it is E left minus E right. If you are talking about reduction potential, then it is E right minus E left. So, one has to keep this in mind while doing the calculation for E cell. So, now for this Daniel cell, one can write E cell is equal to E0 cell minus RT by NF ln activity of Zn2 plus into activity of Cu divided by activity of Zn into activity of Cu2 plus, which then can be written as E0 cell minus RT by NF ln activity of Zn2 plus by activity of Cu2 plus. As for pure metals, activity of copper is equal to activity of zinc is equal to 1, right. So, now one can rewrite this equation in this way. E cell is nothing but E Zn minus E Cu. Now, E Zn is nothing but E0 Zn minus RT by NF ln activity of Zn 2 plus minus ECU is nothing but E0 Cu minus RT by NF ln activity of Cu2 plus. So, what one can simplify from here is that E cell equal to E0 Zn minus E0 copper minus RT by NF ln activity of Zn2 plus divided by activity of Cu2 plus, right. Therefore, these two can be replaced by E0 cell minus RT by NF ln activity of Zn2 plus divided by activity of Cu2 plus. So, what does it mean? We can easily write E0 cell is equal to E0 Zn minus E0 of copper. So, with this one can very easily calculate the standard EMF of a given cell. So, I am giving you one homework to work out what will be the E0 cell for this particular cell. Cadmium solid is in equilibrium with cadmium 2 plus in aqueous medium, and then it is coupled with Fe 2 plus Fe 3 plus system with platinum as electrode. So, from here we will continue in the next class. Thank you.